Log on, tune in, find out. Another good idea from Cambridge.
Okay, so just to remind you what happened those many days ago, I described some conjecture in the modular representation theory of finite groups, Bouret's abelian defect group conjecture, which predicts the existence of certain equivalences of derived categories. And at the end, I give an example of the symmetric groups, and I explained how one could try to, in that special circumstance, introduce a Kac-Moody algebra and therefore turn the problem into one of categorification. Today I'm going to start over from the beginning and just try to explain what I mean by categorification, at least in this particular instance. Okay, so I'm going to talk about categorification of, in the simplest case, for Lie algebras of sl2. So we take the standard basis. That's the standard notation for sl2. The basis consisting of these three matrices, E, F, H, and let's consider a finite dimensional algebra for sl2. Then we can decompose the representation as a direct sum of eigenspaces for the action of H. Okay, the decomposition into weight spaces. All the eigenvalues are integral. And it's going to be convenient to draw pictures like the following in order to describe particular sl2 modules. If we apply E to a vector in the lambda weight space, then we increase the eigenvalue of the action of H by 2. So we draw a picture like this. Okay, F, of course, will do the reverse. And oh, sorry, getting ahead of myself here. Okay, so we draw pictures like this, so forth. Okay, since it's a finite dimensional module, I can integrate to get an action of the corresponding Lie group. So I want to consider a particular element inside this group, which I'll denote by theta. And a formula for this in terms of the E and the F is given as a product of exponentials. Okay, so theta is now acting as an automorphism of the representation V, and it reverses weight spaces. So the restriction of theta to the weight space V lambda is an isomorphism onto the opposite weight space. Okay, now with this setup, let us try to categorify this situation. So what I mean is that we're going to replace the vector spaces by Grothendieck groups of abelian categories. Okay, so we want to interpret the representation space as Grothendieck group of some abelian category. Of course, since the Grothendieck group is an abelian group, and in the cases that we're considering, it usually be a free abelian group, we're going to extend scalars to the complex field in order to get our representation space. So I'll use the notation K with a subscript C to denote this extension of scalars. Okay, so we replace the vector space by an abelian category, and therefore the operators, let's just take, for example, E and F, because they generate, are going to be interpreted as coming from exact endofunctors of this abelian category. So the operators E and F are going to be the classes of exact functors from A to itself. Of course, we need an exact functor in order to induce a homomorphism on the Grothendieck group. Of course, I mean, we could always derive the functor and go to the derived category, but we're going to just assume that we have exact functors in the first place. Okay, and it's also reasonable to assume that there's some adjunctions between these two functors. Okay, so let's assume that E is both left and right adjoint. Why is this reasonable? Well, I suppose that one can put a bilinear form on V such that with respect to this bilinear form, E and F are adjoint operators. So if we interpret the bilinear form as coming from homomorphisms, or HOM, in the abelian category, then it makes sense to impose this condition. Okay, and now the next thing we want to mimic is the weight space decomposition. So let's assume that we can lift the weight space decomposition to the abelian category as well. So we have a decomposition of the abelian category into a product of abelian categories. Okay, which corresponds to the weight space decomposition. So the Grothendieck group of this piece is just the lambda weight space of B. Okay, so that's quite a reasonable seeming way to enhance this representation. Okay, and then a question arises as to what do we mean by integrating the action, and in particular, how do we interpret the action of this theta? Okay, so this is now a automorphism of the should be interpreted as an automorphism of the Grothendieck group, right? And the easiest way to get that would be as coming from an equivalence of the abelian category, a self-equivalence of the abelian category. But if you take a look at the formula for this automorphism, you see that involves some alternating sums. So this is a hint that it's not really reasonable to expect this automorphism to be induced by a self-equivalence of the abelian category A, but rather of its derived category, right? Because remember that we can also interpret this Grothendieck group as the Grothendieck group of the derived category of A. So what we'll want to we want to set up things in a way such that we can interpret theta as coming from the self-equivalence of the derived category of A, which restricts to the derived category of the various weight spaces, and gives equivalences between the derived categories of opposite weight spaces in the abelian category. Okay, in order to make this work, we find that we have to have a little bit more structure. Okay, so to actually get this last bit, this lifting of theta, we find, or at least we need some additional structure. That turns out to be the action of affine Hecke algebras on powers of the functors E and F. Okay, so this is the additional information that this process of categorification gives us. Once the linear transformations become functors, then we can talk about endomorphisms of the functors, okay, and have this additional input. Whereas before, it doesn't really make sense to talk about endomorphisms of the linear transformations. Okay, and I mean, next week, Ruquier is going to talk about this categorification story from a more sophisticated and abstract point of view. And from that point of view, the lifting of this reflection is perhaps not such a key part of the whole story. But I suppose we set this up because we had particular applications in mind. You know, the construction of certain derived equivalences. Okay, which I gave one example of on Monday. So the motivation is the construction, or I suppose the systematic construction of, I guess, interesting equivalences of derived categories. Such as the ones that we require for Bourret's conjecture. Okay, so the way we usually get examples of categorification of, say, sl2 or of other Lie algebras is we have examples in mind. For example, the symmetric groups. And we find that when we pass to the Grothendieck group, so a sort of decategorification, we get these actions. But here I'm taking the opposite viewpoint, at least for the time being, where we just kind of suppose we didn't know any of these examples and we just tried to construct by hand such examples. Then we would write down some very small and silly looking things, and that's what I'm going to do now. Okay, so I'm going to construct examples where the abelian categories are usually categories of modules over algebras over a field. So let's just fix a field. Okay, and in the first example, okay, I'm going to take the category of vector spaces, finite dimensional vector spaces, over the field. I'm going to take 2 copies of it. Okay, and then just consider the identity functor in both directions. So of course, when we pass to the complexified Grothendieck groups, well, I mean, every vector space is the direct sum of one-dimensional vector spaces. So the Grothendieck group has rank 1 and just records the dimension. And of course, these functors just become the identity map on the Grothendieck group. Okay, and of course, one can see that this is indeed a 2-dimensional sl2 module, okay, where the weight spaces h acts by -1 and 1 on these 2 copies. I guess maybe I should write the identity map. Sorry? I guess, I mean, E is acting by, yeah, so maybe I shouldn't write equals, but the action of E is by the identity map here. I'm using these kinds of pictures here. Okay, so implicitly, for example, if I apply E to this part, then I get 0. Okay, so it's nilpotent. You apply E once, and then twice you get 0. Does the picture? Oh, this one here. Okay, right. So the little e just means that I take the class of the big E in the Grothendieck group. Okay, so since it's the identity, yeah, maybe I'm going to have multiples of the identity later, so I wanted to avoid writing it, but yeah. Is that it? So this is the identity functor on some abelian category. So on the Grothendieck group, it will also be the identity. Wow. Okay, sorry. Okay, so let's take a second example. That worked out pretty well. It was kind of trivial, but well. So let's try let's try doing 3 of those guys. Okay, so, well, what kind of choice do we have? I'm sorry? Theta, I guess, yeah, it would also be the identity, yeah. Okay, here, let's see what sort of choice we have for this functor. Well, since these are semi-simple categories, the only choice we have really is some direct sum of copies of the identity functor. Okay, so this is just going to multiply the dimension by some integer m, say. Okay, this is the only possible choice. And of course, then this one, since we asked it to be adjoint to this functor, right, will also have to be the identity that number of times. Okay, so when we go to the Grothendieck group, this is going to be multiplication by m, and so is that. Okay, and because of this picture, the way I've drawn it, E is going up. The weight spaces are going to have weights -2, 0, and 2. Right, this is hoping to be the 3-dimensional irreducible module for SL2. Okay, but what happens if we apply F and then E here? okay, we should get, because the weight space is 2, we should get multiplication by 2. So we need to have m squared is equal to 2. And that's going to be a problem. So this is really no good. Okay. So let's try again. So we have to introduce, in order to fix this problem, we have to introduce some non-semi-simple algebra. Okay, so we're going to take in the middle modules over k of x modulo x squared, two-dimensional algebra. Okay, and then a natural way to connect these is by inducing and restricting. So when we go up, we induce. And when we go down, we restrict. Okay, and now when we pass to the Grothendieck group, okay, I suppose we should choose a basis. What is the meaning of 1 here? We need to choose a basis for this. So we just take the simple modules as a basis for the Grothendieck group. So for example, if I take the simple module here, which is one-dimensional, and I restrict it, I get a one-dimensional vector space. So this is going to send the generator to the generator there. Okay, however, when I induce the simple module here, I get the free module, okay, which has 2 composition factors. So this is going to be multiplication by 2. Okay, and this one you see is going to work. Okay, so that's fine. Let me just remark that you can do a variation on this one where we can interchange the roles of K and the 2 algebras in example 2. So I can have K of x modulo x squared on the 2 ends and category vector spaces in the middle, and you can check that that works out just as well. Here, the 2's and the 1's get interchanged. Okay, but I suppose if you know something about dual canonical bases, you'll see that one of these is better than the other. Okay, but we'll see another reason why one is better than the other when we go on further. Okay, now let me just quickly write up now a 4-dimensional module. Consider k of x modulo x cubed. Okay, later we'll see that there's more sophisticated ways of constructing various representations, but now I'm just trying to do really things by hand. Okay, so we take B twice, and then we could put the category vector spaces on the ends. Okay, and again we take the obvious functors on the ends. Okay, in the middle here we have to take, let's consider taking a tensor product with a bimodule, which I'll call Z. Okay, Z here is the kernel of the multiplication map. Okay, this is a map of BB bimodules, so the kernel is going to be, again, a BB bimodule, and we use this to write down a functor. Okay, the adjoint, of course, is some Helm functor, but as it turns out, it's also isomorphic to the original tensor factor. Okay, so I'll leave you to check that. That induces an action of sl2 on the Grothendieck group, which is a 4-dimensional irreducible module. Okay, so you could try to go on now and try to do, say, the 5- and 6-dimensional one, but already the next example is quite difficult to construct in this extremely naive way. Okay, now let me do an example which comes from the symmetric groups. The example from Monday. Instead of doing the whole thing, the whole sum of all the symmetric groups, I'm just going to pick out a little piece so that, again, you can see how it looks more explicitly. So I'm going to take the characteristic to be 2 and just take certain blocks of certain small symmetric groups. Okay, so let's take the group algebras of S3, S4, S5, and S6. Okay, of course, these are connected by induction and restriction functors. Okay, but this can't be an SL2 module when we pass to the Grothendieck group because S3 has only 2 simple modules and S6 has many more. So I'm going to need to take some blocks. So I'll take certain blocks of these. Okay, so it takes certain summands of these. If one knows the combinatorics of the symmetric groups, I could describe in terms of the combinatorics which blocks I'm taking. But I can also say that here I'm taking the each of KS3 and KS6 has a unique semi-simple block. So here I take the matrix algebra summand, the simple block. Okay, and here I take the so-called principal blocks. Okay, these are the blocks which have, each of these has a unique block with largest possible defect group. Okay, so well, let's just say we take certain blocks here. So these are the principal blocks. Okay, and one can still make sense of these functors. One just has to compose them with functors that go between the whole group algebras and the blocks in the obvious way. And when one does this, one gets indeed a representation of SL2 in the Grothendieck group. And it looks like this on the standard basis of simple modules. So I have like this. Okay, so you see it's going to be the sum of 2 irreducible modules, a 4-dimensional one and a 2-dimensional one. And the matrices in terms of the basis of simple modules is as follows. Let me just write down. Okay, and you can check again that this gives an action of SL2. Okay, but perhaps the most interesting point is that even though this is irreducible as an SL2 module, it is not irreducible. I'm sorry, it's reducible in the sense that it's a direct sum of 2 irreducibles. Once we go to the abelian categories, then there's no such splitting, right? These are blocks, right? So they can't be decomposed any further. Okay, but we'll see later that a replacement, even though we don't have a, this is not the direct sum of the two irreducible constituents. It's something like an extension. Okay, so this should be regarded as an extension of example. This is an extension of example 4 by example, the two-dimensional one, 1. Okay. Okay, now I'm going to do a different sort of example now where I do have some kind of special knowledge beforehand. And this is the category O for GLN. Okay, so we take G to be GLN, and we consider the subalgebras of diagonal matrices and of upper triangular matrices. Okay, and then we consider the category of finitely generated modules, which are diagonalizable over H. And such that the submodule generated by any, the n submodule generated by any vector is finite dimensional. So it's locally n finite. Okay, so this is just the BBG category O for GLN. Okay, now suppose we have such a module. Okay, then it's given by some action map GLN tensored with M mapping to M. Okay, I can also view this action map as a map of GLN modules, right, where I view GLN as the adjoint representation of GLN. Okay, and when I do this, I can rewrite GLN as the tensor product of the natural representation with its dual. Okay, and then I can take the adjoint of this map. I can move the W star to the other side to get an endomorphism of W tensor M, which I'll call L M. Okay, so the way to think about this is that I have a functor which takes any object of the category 2, that object tensored with a natural representation. Okay, but I get for free a natural transformation of the functor. Okay, so this should be thought of as some analog of the Jusis-Murphy operator in this context. I'm sorry? The JM element, which Sasha talked about in his. So just as we did in the case of the symmetric groups, we can use this JM element to split the functor into subfunctors as a direct sum of subfunctors. So we define, say, EA M to be the 8th generalized eigenspace for the action of Lm. Okay, and this decomposes W times M into its into a sum of generalized eigenspaces. Okay, and in a similar way, or just using the adjointness property, one can consider the functor of tensoring with the dual and write this as a direct sum of functors Fa. Okay, and then one can check that if you consider the classes of, for any A, the classes of EA and FA on the Grothendieck group will give an action of SL2. Then in fact, much more is true. If you restrict to the case where A is integral, then you're getting an action of SL infinity. Okay, and so this is, again, very much analogous to the construction of the Fock space in the symmetric group case. Okay, but I wanted to use this example to show how the affine Hecke algebra, which I mentioned at the beginning of the talk, arises in a somewhat unexpected way. Okay, in the case of the symmetric groups, since we can regard the symmetric group as a quotient of the degenerate affine Hecke algebra, it's not so surprising that through the Drusus-Murphy elements, the degenerate affine Hecke algebra is involved somehow. But here we'll see it arising in a more surprising way. Yeah. Yeah, I don't know. I suppose you could try to do something similar for. You mean for other types? Or? Yeah, I haven't thought about it, but it seems possible. Okay, so let's consider So some sort of other kind of object acting, maybe not. Yeah.
And another question. So there is another way to compose this tensor product function according to generalized.
Yes, using the block.
Characters.
Yes, that's right.
So
Yeah.
does it have something to do with this decomposition?
It's the same one. Yeah.
So, but then somehow. Okay, perhaps we can stop it.
Okay, sure. Okay, so maybe the observation to make here, as I mentioned, this functor of tensoring with W comes naturally equipped with this endomorphism, and since we defined these summands in terms of generalized eigenspaces, then of course the endomorphism still acts. So we see that the functor, so by construction, the functor E is equipped with a natural transformation X let's call it, x from an endomorphism of this functor, where the action of x at the object M is given by L M. Okay, I'm going to normalize a bit here to make the operator nilpotent. I'll just subtract off the eigenvalue. Now, so that's some extra structure, but there's even more, which comes from applying this functor of tensoring with the natural representation twice. So if we start with a module and we tensor with the natural representation 2 times, then of course we can interchange those 2 factors. Okay, and a natural question to ask is, how do t and x interact? What I mean by that is when we consider this module W tensor M, we have x acting through the Jusis-Murphy type elements L in 2 different ways. Okay, and we also have t. How do these 3 things interact? Okay, and the answer is given by a calculation done by Arakawa and Suzuki, which I'll turn into an exercise. Okay, so we want to consider 2 different endomorphisms of W, W tensor. Okay, the first possibility is to apply this T, I guess I should label it by the module M, Tm. Okay, and then afterwards we're going to apply the L, which is associated to W tensor M. Okay, so this module is obtained by taking W tensor M and tensoring with W. So I get this operator L. Okay, we could also do, we could take the endomorphism Lm, okay, just of W tensor M, okay, and then just extend it by the identity on W. Okay, and compose that with, again, T. Okay, and it turns out that these 2 differ by the identity map on this module. Okay, and if you can see here, this is really the relation in the degenerate affine Hecke algebra, which is appearing here. This, once we shift the scalar, is going to be an x. Okay, and this is going to be another x, but an adjacent one. Okay, and this is precisely, therefore, that relation that Sasha wrote down. Okay, so that brings me to the definition then of that Ruquier and I developed in order to get the derived equivalences, which we called sl2 categorification. Maybe I should say that, I mean, from this exercise, it follows that the endomorphism T, that T restricts the T, which we can view as an endomorphism of the functor, which takes a module and tensors it twice with the natural representation, restricts to an endomorphism of just the square of the A for any A. so now let me say what sl2 categorification is. Okay, so we have the ingredients are a k-linear abelian category. Okay, and let's assume that it satisfies a ascending and descending chain condition. So it has composition series. And as I mentioned at the beginning, we want to have exact functors such that we have adjointness by adjointness of course, we need to have the sl2 action induced on the Grothendieck group. Okay, sorry, I'm repeating what I wrote at the beginning. So I guess in some of the examples, I don't actually have a finite dimensional model. Okay, but I suppose I want it to be integrable. So, okay, so it induces a locally finite action of sl2. Okay, and finally, I have a weight space decomposition. Which corresponds to the abelian category, which corresponds to the weight space decomposition of the sl2 model. Okay, and then the extra information which gives us the possibility of constructing the derived equivalences. Yeah, is that right? Are the information of the natural transformations which I saw arising in this example. Okay, so we want also and some natural transformations x of E and t of the square of E. Okay, such that the t should satisfy some kind of braid relations. So first, it should square to the identity. Okay, now if I consider the third power of E, okay, then I can use t to act on either the first two or the second and third copies. Okay, so I write down therefore a braid relation. Okay, so if I have t acting on the first two copies, and I can consider also t acting on the second and third copies. of course, this equality takes place inside the endomorphism ring of E cubed. Okay, and then I have this relation which we saw here in this calculation, which is that T composed with x applied to the second E is the same as x applied to the first E composed with T plus the identity, or is it minus? Oops. Okay, there's always a question of whether it gets shifted. Oh no, I think it's right, minus. It's consistent, I think. Okay, and then finally, we ask that the x is locally nilpotent. Okay, so on any object M, xx nilpotently. Okay, we rearrange this to be the case here by just shifting the scalar, and even though this identity was checked with the L's, you can see that by a additive shift, this relation will still hold. Okay, and well, the purpose of these relations is really to give these actions of the degenerate affine Hecke algebra. And that's what one uses to construct the derived equivalence. So maybe I should state the result first. So the action of theta lifts to an equivalence of the derived category, a self-equivalence, which restricts on weight spaces as expected, I guess. This restricts automatically to derived equivalences between opposite weight spaces. That's right, yeah. But I guess one has to be careful, and this is what this construction, I should say, the construction of this lifting is due to Ricard. He did it in the symmetric groups. He wasn't using the language. I suppose at that time we didn't know about the Kac-Moody algebra. So he was doing it using a different sort of combinatorics. But essentially the construction is due to Ricard. Okay, so I think I just have. I think I'll have to leave the construction of the derived equivalence to next time. But first, let me just say how one gets a start, and that's through the action of these affine Hecke algebras. Okay, so recall that from Sasha's lecture that we can define the degenerate affine Hecke algebra. Sasha used this notation both for the non-degenerate and degenerate versions. Here, for convenience sake, I'm just using the degenerate cases. So we have generators t1 through tn minus 1 and x1 through xn, subject to various relations, which when imposed is at least gives you the structure, at least as the vector space of, I mean the t's generate a subalgebra isomorphic to the group algebra, and the x's give you some polynomial subalgebra. And then you get an interesting relation between the t's and the x's. Okay, and then we can use our endomorphisms to get our actions on powers of e's and f's. So we get a homomorphism from the degenerate affine Hecke algebra into the endomorphism ring of the functor e to the n as follows. We well, ti t we know acts on a square of e, but we can place powers of e before and after this square of e. So in this way, we can take any two adjacent copies of e inside the nth power and apply t to it. So we get t on this part and the identity on the other parts. Okay, and this we can define to be the action of ti, the generator ti. Okay, and similarly, xi is going to be just the action of x on the ith factor of e to the n. Okay, and then it's easy to see that one gets the that this is indeed a homomorphism. The braid relations between the t's are given by this identity, and of course you have this identity. So you get this copy of the symmetric group by t here. Notice that the t's which are far apart commute automatically because they're acting on different factors. Okay, similarly here the x's commute, giving you this the action of the polynomial subalgebra. And then the interesting relation is this one here. Okay, so that translates into the relation t I x. Is it I plus 1? Is equal to x I ti minus 1. Okay, and once one has this action of the degenerate affine Hecke algebra, then really allows you a lot more flexibility in building functors out of the e's and the f's. So I'll say in sorry, let me just have 2 more minutes. This, if we write down the formula for the exponential, it's going to be some large sum. Let's see, so minus 1 to the a plus c over I factorial, j factorial, k factorial, e to the f to the I, e to the j, f to the k. Yes, correct. This one's easier. Okay, so it's easy to interpret these guys just as powers of the e's and the f's, but we need to divide by, we need to construct some divided powers. And to do that, one uses the representation there of the affine, degenerate affine Hecke algebra to cut those functors. And finally, one constructs a complex. Okay, this is not quite right, but the idea is that you use the summands here as the terms of the complex, and then use the adjunction between E and F to construct the maps between them. Okay, and I'll say more about how one gets this to work tomorrow.